So I'm here to introduce our next speaker, Geordie Williamson, who is probably already well known to most of you as someone who fundamentally revolutionized the way we think about modular representation theory, and his pioneering won't be recognized by many prizes, including the European Mathematical Society Prize and, of course, the Clay Research Award here 3 years ago. I thought it would be very boring for you if I gave you a complete list of prizes awarded to Geordie and also the list of prizes that should have been awarded to Geordie. And so instead, I think we maybe I'll mention one fun fact. That's also not so easy because Geordie is a man of many surprises, both in mathematics and outside of mathematics. But how about this? He was once in a very interesting commercial. And now, lest you get distracted from his lecture by searching for this commercial on the YouTube, it's rigorous research shows it's not there. And so, but it was filmed in China. Geordie played the part of reputable doctor, and the commercial was for laxative. So please, please welcome Dr. Williamson.
Thank you very much. I remember I had to learn the phrase in Chinese, and so the product is called Xiliting, I think. So just another advertisement. We've just, thanks to some very generous donations, we've started this research institute in Sydney. So if you would like to conduct research in Australia with somebody based in Australia, doesn't need to be in Sydney. So if you'd like to visit Australia for a few months, please consider applying to our institute. That's the ad break over. I would also like to apologize for these slides. Directly after leaving Australia, I was in Rome and I tipped a cup of tea all over my laptop. So that was 2.5 weeks ago. And so I've only recently been reunited with a laptop. And so these slides are very unusually structured. But if you're willing to, if you want to see these slides ever again, you can write oxford.pdf at the end here, and you can download these slides. Okay? You may not want to, however. Okay, so I'm talking about challenges in modular representation theory. These are the challenges. Okay. I'm sorry, but I had to prepare these slides without a laptop. So these are the challenges, and I forgot to turn the mic. So we're interested in describing the simple representations of symmetric groups in characteristic P. So you might know that in characteristic 0 over the complex numbers or the rational numbers, we have a very good theory, partitions, Young tableau, very useful, very easy theory. We would like to extend this to characteristic P, and we don't know very much. However, what we do know suggests that there is an incredibly rich world waiting for us. Also finite groups of Lie type, so most simple groups are close relatives of finite groups of Lie type, something like GLNFP or SP2NFP. And in this talk, we're only considering the equal characteristic representations of these groups, so we're looking at their representation theory in natural characteristic. These are finite groups, so we could also look at the representation theory in characteristic L, where L is not P. We're not doing this in this talk. Or we're looking at the irreducible representations of reductive algebraic groups. So these are algebraic representations, and somehow these two are very, very closely linked. And so mostly I'll be concentrating on this. So I'll concentrate on this for most of the talk, and then at the end I'll talk about an application to this. And you have to believe me that these two are connected. And often in representation theory, we might ask for a list of irreducible representations, a classification. And in these problems, we have a classification, and we've known this for some time. But what we're interested in is the finer structure. So, for example, dimensions, character formulas, descriptions of categories, etc. Okay. And so these are the challenges. What I want to tell you in this talk is a story which connects these questions to the topology of singular complex algebraic varieties using the theory of perverse sheaves. So there's some topological avatars of these questions. And I also want to explain, which I find very beautiful, and I think it's not as widely known as it should be, that these questions are some tiny slice of the geometric Langlands program. Okay? And this is encapsulated by something that I actually won't outline in detail, which is Bezrel-Kamennikov's equivalence. But there's some equivalence of categories that is lying under all of this that's extremely powerful. And somehow, it seems remarkable to me that these questions that we spend so many years working on are some tiny, tiny piece of a bigger theory about which I know very little. Okay. So I just want to start with a challenge for you, which is, what is this picture? And this actually happened to me a few days ago. I was sitting in the physio and someone sent me this picture and said, what is this picture? I was waiting on the phone. So maybe you know the answer, maybe you don't. I'm kind of interested. Is it obvious to 50% of the audience what this picture is, or is it obvious to nobody?
Pascal triangle mod 3?
Yes. Pascal triangle mod 3. Okay. And it's very nice. You can actually do this picture for the one that my friend sent me actually was Pascal's triangle mod something like 35 or something. And then you get kind of two of these pictures laid on top of each other. It's a little bit more tricky. What's this picture? So this is the 3 valuation of Pascal's triangle. Okay, so the lightest dots here are valuation 0, which are exactly the dots that exist here. Okay, so that's the answer. This is Pascal's triangle modulo 3. And here's the valuation modulo 3. And somehow I want to use these two pictures as some kind of image that you should have in mind for what representation theory looks like modulo P. So let me explain. I want to firstly recall the highest weight classification of representations of a compact Lie group. So we consider a compact Lie group and we take a maximal torus. And we have this Lie theoretic data associated to this. So we look at the way that the maximal torus acts on the Lie algebra. This gives us a set of roots, which are a subset of weights, which are characters of our torus. And these all sit in the dual of the Lie algebra of our maximal torus. And so we get a picture like this of the dominant weights. And these dominant weights classify all irreducible representations. So for each one of these weights, there's an irreducible representation. And these are all pairwise non-isomorphic. So a simple example is, probably the most beautiful example is just taking SU2. So the maximal torus is S1 of diagonal matrices. The quotient is S2, which has a complex structure, is P1 of C. And then the simple module is realized as the global sections of a holomorphic line bundle on the projective line. And this is true more generally by the Borel-Weil theorem. To any dominant weight, we can associate a line bundle on this space. This space is actually has a complex structure. We take global sections and we get this simple module. Okay, so that's highest weight theory. And the example of SO3 is the conference poster. So here we have the, so this is like the picture for SU2 where every second line is missing. So this is the spherical harmonics for SO3. So these are the analogues of Fourier coefficients on the two-sphere. Okay? And if you would like, you can kind of think about what these pictures actually mean. Okay? But these are some picture for a basis of an irreducible representation of SO3. Okay? And I'd like to thank the organizers for choosing this picture for the... Okay, so what happens in characteristic P, if we take an algebraic group, reductive algebraic group, we choose a Borel subgroup and a maximal torus, and we get exactly the same data as for a compact Lie group, namely we get roots and weights, and we get the same picture. And we can do the same thing. We can define this line bundle on G mod B and take its global sections. And we get something that we often denote by nabla. And the only difference here is that this module is not irreducible in characteristic P in general, but it has a simple socle. So it has a unique simple submodule. And Chevalier's theorem tells us that the parameterization of the irreducible modules of an algebraic group in characteristic P is the same as in characteristic 0, but here we need to take a submodule of something. So we have something that's given to us in an explicit way, but we have enormous difficulty actually understanding what this socle is. Just go to the next slide. I'm sorry I can't do, you're kind of forbidden from looking at this for a second. Okay. So if P is the characteristic of K, if P is 0, then this is irreducible. And so the socle is just this nabla module. And then we have the Weyl dimension formula and the Weyl character formula, which can be proved in many different ways. But we have a very clean answer, very useful answer. And if P is bigger than 0, so if we're in positive characteristic, and large, we have something called Lustig character formula, which is orders of magnitude more complicated. But, and somehow a lot of what we do is trying to understand precisely what this formula means. And also it's only valid for in large characteristic, and so we would like at the end of the day to also understand for all characteristics what happens. And just to give you an example, so back to this example of SL2. So here I'm listing the, here I'm telling you what the socle is inside homogeneous polynomials of degree I. So here, this is irreducible. This is the natural representation of SL2. This is the adjoint representation of SL2, which is irreducible in characteristic 3. And here is the kind of interesting line. This is where the interesting business starts. If I imagine x cubed, and I act on it by SL2, I send x cubed to some linear combination of x and y to the 3. But now I'm in characteristic 3, so I can pull in the 3 by the freshman's dream. And I get that this is a submodule. Okay? So this is the first example where we see that that these induced modules, these nabla modules can have interesting behavior modulo P. And if we just look at this picture and just draw dots where we have, so all in the case of SL2, all these spaces are of dimension 0 or 1, then we get exactly the same picture as before. Okay, so this bit here is the very top of this. So here, that was the calculation we just did up here. Okay. And you can also ask, what was this picture with the valuations of binomial coefficients? And this is something called the Janssen filtration, okay, which is very... So these pictures are meant to tell you that, kind of motivate that we expect a kind of fractal-like behavior of characters and categories. So this is very much related to the existence of the Frobenius map. So in an algebraic group in characteristic P, we have an endomorphism of algebraic group which raises coordinates to the pth power. And somehow, just by pure thought, you can convince yourself that the representation theory has to look quite different just because you have this Frobenius. It can't look the same as in characteristic 0. And I think that there's some philosophy which is that kind of everything in the representation theory of an algebraic group in characteristic P comes from this Frobenius, but that's difficult to make precise. And the other thing, so this will be less of a focus of these slides, but there's a philosophy of generations where you kind of seek, so in a fractal you might seek a blueprint from which to produce the whole fractal. And in the representation theory of an algebraic group, you might seek some kind of blueprint that then repeats itself. And this is tied up with the philosophy of generations. But yeah, I won't go too much into this in this talk. So I want to explain how we can connect representation theory to constructible sheaves and topology. And to do this, I want to explain a little bit of the very basics of Langlands duality. So the Langlands dual group is an absolutely fundamental object. So the definition that I'm sure you've seen in other talks, but that we kind of learn is that reductive groups are classified by reductive groups over an algebraically closed field are classified by some combinatorial data that is independent of K. So we have a weight lattice, the characters of the torus. Inside that we have a set of roots. We have the co-weight lattice, the co-characters of the torus, and inside that we have a set of co-roots. So you can think about any reductive algebraic group is somehow made out of SL2s and PGL2s and tori, and this is kind of how you glue them together. And there's a symmetry on this data which leads to the Langlands dual group. So we say, if you want to know what the dual group of a group is, you say, okay, we work out what this data is, and now we swap it and appeal to the classification and say, okay, that's the group. Yeah? But it's a kind of strange thing to do in some sense. So here's some examples. So SLN, the Langlands dual of SLN is PGLN. GLN is self-dual, so that often in representation theory, people don't notice Langlands duality because they work with GLN, and then you see it when you first go to another group. And Langlands dual of symplectic group is orthogonal group. So probably the most important thing here is for a torus, the Langlands dual of a torus is just the same torus, but not canonically. It's the torus that has as co-characters the characters of your original torus. Okay. So now here's a caricature of the Langlands correspondence, and I hope nobody murders me after this slide. So what are the most important features from a kind of looking from a great distance at the Langlands correspondence? So firstly, we have G on one side and G check on the other side. So we have a group and the dual group on the other side. On one side, we have homomorphisms, all homomorphisms with some adjectives from something to do with the Galois group into G check. Okay. So all here, and somehow you should think about G check might be something like SL2 or something, so it's pretty small and you're trying to fit something very complicated in something very small, and that's very hard. And we consider these up to conjugacy. On the other side, we consider irreducible, not all, irreducible representations of G of something to do with K, up to isomorphism. And so this is kind of the world of arithmetic, this is the world of analysis, and here these are generally enormous. So here the things are very small and complicated because they're very small, and here they're very large. And both sides are very tricky, but in different ways, and that's why it's so useful, because something that's difficult over here might be easy over here, and conversely. And just in case, so this is a toy example of the Langlands correspondence, but it's really not Langlands correspondence, but I think it's useful motivation, is if we consider our compact group from earlier, I want to explain how the highest weight classification can be seen as an instance of something fitting into Langlands duality. So we've seen before that the irreducible continuous representations of our compact group are classified by highest weight. So this is the Weil theorem that I stated before. But dominant weights or highest weights are just representatives for the quotient of the weight lattice modular of the Weil group. And the characters of this group are canonically the co-characters of the dual group. So this is just by definition of what the dual group means. And here I've just continued my W. And this is the statement that any homomorphism, any algebraic homomorphism from C star into G check has to land in some maximal torus. And so we can put it into our normal maximal torus, and the ambiguity is precisely W. Okay. And so here we have irreducible representations of something classified by certain homomorphisms up to conjugacy into the dual group. Okay. So that's a non-real example. And this is the first real example, is the unramified local Langlands correspondence. It's a very beautiful thing. So on the right-hand side, we consider homomorphisms from the integers into G check, so the Langlands dual group over the complex numbers. And again, we have to put adjectives with semi-simple image up to conjugacy. So this is just the same thing as a conjugacy class of semi-simple elements in the dual group. So this is a rather simple set. On the other hand, what local Langlands correspondence tells us is that this should be the same thing as certain representations of this topological group. And so these are a priori enormous and complicated. So this unramified refers to the fact that it has a geo fixed vector. So this is the maximal compact subgroup. And this bijection follows from something called the Satake isomorphism, which I remember I first learnt in some notes of Dick Gross when I was a graduate student. So this is some kind of Hecker algebra of maximal compact bi-invariant functions on our group. So this is something a priori very complicated, but Hecker algebra theory tells us, so this is precisely the thing that acts on GO fixed vectors inside here. So if you take a representation and you look at fixed points, fixed vectors under a subgroup, then the thing that acts is the Hecker algebra. So and then the Satake isomorphism gives us an isomorphism between this and the complexified Grothendieck group of the dual group. And you can see that this side is characters of this, and this side is characters of this. Okay? And so we have this isomorphism that underlies this bijection. So it's a very nice exercise, if you haven't seen this, just to convince yourself that a character of this is the same thing as a semi-simple conjugacy class. So I just want to, so this is a piece of the local Langlands correspondence. This is the easiest piece. And somehow I want to just give you the following slide. So here you imagine geometric Langlands as some enormous thing that I don't understand. And it looks a little bit like a planet of higher genus. And what we do is we zoom into a small point on this planet, and that's where local Langlands exists. And we imagine local Langlands as being a sea in which the further we go down, the more difficult it gets inside this sea. And somehow these two layers right at the top of this sea are extremely interesting. So this is where we'll be spending our time. On the very top of in this ocean at a very small point on this big planet. Yeah? And probably you're asking, where is Bezrel-Kamnikov in all this picture? I mean, it's a very natural question. And Bezrel-Kamnikov is out where the air is thin. Okay. So now we want to categorify the Satake isomorphism. So yeah, so some motivation for why we want to do this. So in Langlands correspondence, you have some set is in bijection, hopefully canonical, with another set satisfying a whole list of properties. So it's a bijection of sets. But then in geometric Langlands, the goal is, in the case of a function field, to upgrade this to some equivalence of categories. And so this is a fundamental isomorphism underlying a very, very small piece of local Langlands correspondence. And we would like to upgrade, so this is obviously a Grothendieck group of something, namely representations of the dual group. And we would like to upgrade this to something. Now, the first observation is that, of course, we can just quote, so a bi-invariant function is the same thing as an invariant function on one side. And now this, so we want to categorify this, and it seems remarkable to me that now we say the word categorify, and everybody has some idea of what it means. But actually Grothendieck was advocating this a long, long time ago with his function sheaf correspondence. So what Grothendieck says is that if you have some interesting function defined on the rational points of an algebraic variety, then it should be some shadow of an object, namely some kind of sheaf, where we get the function by taking something like Euler characteristic of a stalk or trace of Frobenius or something like this. And so somehow Grothendieck was advocating categorification a very long time ago. And so the point is that this can be realized as the points of some algebraic variety, or not an infinite dimensional algebraic variety. Okay. And that's what I'll explain now. So this is the affine Grassmannian. So now I switch gears a little bit so I can draw pictures to the complex coefficients, but there's no actual technical need to do so. We could also work over a finite field. And the observation is that this is naturally a topological space, but it's actually an infinite dimensional algebraic variety. So it's a direct limit of algebraic varieties under closed embeddings. And the kind of simplest example of an infinite dimensional variety is like P infinity of C. Okay, just direct limit of all projective spaces under some natural embeddings. And the most important kind of basic fact about this space is that if we look at the geo orbits on it, it's naturally parameterized by dominant co-weights. So back in the, over here, the irreducible representations of this are parameterized by exactly the same set as parameterizing the orbits here. Okay? So at least at a very basic level, these two, this space and this category has something in common. Okay. So just two examples. So if I take G to be C star, then the affine Grassmannian is, we should evaluate this on Laurent series, so we get invertible Laurent series, modulo invertible power series, and the only invariant of this is the valuation. And so we get that this is just a discrete set Z. And note that even this is not an algebraic variety. It is, however, it's a direct limit of algebraic varieties. Namely, I take 1 point and then a few more points and then a few more points, etc. Okay. The second example is SL2. So if I wanted to fool you into thinking you understood this space, I'd just tell you it just has one complex cell of each dimension. Okay. But so this looks very much like, for example, infinite projective space, infinite dimensional projective space, but in fact it's rather complicated in terms of how these spaces are glued together. So this is the first example, probably the only example that one can draw. So the closure of C2 inside this space, so if we close up C2 inside this space, we get this complex surface. So here's a real picture of it. So it's a smooth surface. It has a unique, it's smooth except for at 1 point, and it has a unique singularity here, which is an A1 singularity. So if you're an algebraic geometer, this is what you get when you take a second Hautzebruch surface and contract a -2 curve on it. Okay? And then you have to imagine that to get this affine Grassmannian, we now glue on a C3 onto that in a complicated way, and a C4 onto that in a complicated way, etc. So that's the affine Grassmannian. And the geometric Satake equivalence, so on this affine Grassmannian, so this space is a direct limit of complex algebraic varieties, of projective algebraic varieties. And what we want to consider is some category of constructible sheaves, some category of perverse sheaves on this space. And on an infinite dimensional space, that is generally problematic. But we just declare that a perverse sheaf on this space is a sheaf that's supported on some closed sub variety. So one of these finite dimensional closed sub varieties. So for example, in this example, a perverse sheaf on this space is just a sheaf on Z that has finite dimensional stalks and is supported in one of these finite sets. So it has finite support. So it's just a finite dimensional graded, Z-graded vector space. And here you have to imagine some constructible sheaf living on this. Okay. And kind of no part of this story is particularly easy or easy to explain, but so the most important probably property of this category is that it has this tensor product. So generally a category of perverse sheaves will not have any reasonable tensor product, but this does, which imitates, so this tensor product imitates multiplication of, so convolution of functions in a Hecke algebra. And this turns out by a miracle to be a symmetric structure. So it's like a tensor product of vector spaces. There's a symmetry. And there's an equivalence with representations of the dual group. And another aspect of this is that, so actually how this equivalence is established is by noticing that you have the so-called fiber functor. So given any perverse sheaf, we can take its cohomology and produce a vector space. And on the other side, we can just take our representation and forget that it's a representation and produce a vector space, and this diagram commutes. And this equivalence, if we do it over a finite field, it can actually be used to deduce the Satake isomorphism. So it really is a categorification of this isomorphism in the strongest sense. Another interesting aspect of this is that we want to study the representation theory of this group, and as we vary K, the representation theory varies in rather subtle ways, as we already saw in this fractal picture. So the size of the fractal depends on the prime. And somehow that's reflected over here. This space doesn't change. All that changes is the coefficients. And so somehow there's very subtle torsion phenomena in this variety that precisely reflects this change. So this is a cornerstone of geometric representation theory, a cornerstone of geometric Langlands, but it's also more recently showed its head in the classical Langlands correspondence. So this recent remarkable work of Vincent Laforgue crucially uses this. So this is in the Langlands correspondence for classical Langlands correspondence for function fields, and it's also relevant to the local Langlands correspondence. So it's something dear to our hearts in geometric representation theory, but it's also more broadly useful. Okay. So the following slide is a little bit chaotic, but so I just want to try to illustrate how remarkable this is, even in this kind of simplest possible case. So one of the things that perverse sheaves do, so the simple perverse sheaves are intersection cohomology complexes, and if we take cohomology, remember I said over here that cohomology is the underlying vector space of my representation. If we take cohomology of an intersection cohomology complex, we get intersection cohomology. Okay? And so if we look over the rational numbers, these varieties giving us the irreducible representations are just a disjoint. So over the rationals, in this particular case, intersection cohomology is just equal to ordinary cohomology. And we have one cell of each complex dimension. And so this recovers the picture of the representation theory of SL2, for example, on the Clay Research Conference poster here. But on the other side, so there's a very important aspect of intersection cohomology is that it does not satisfy the universal coefficient theorem. So it's very tricky in principle to work out this with coefficients in K. And if we start working out this in these intersection cohomology groups with coefficients in, for example, a field of characteristic 3, then we get precisely this Pascal's triangle again, the Pascal's triangle modulo 3 showing up. Okay? So even in this reasonably simple example of PGL2, there's some remarkable phenomena showing up. So just another point of view here is that, so if we consider the complexification of a compact group, so we assume G is the complexification of a compact group, then one can show that the affine Grassmannian is in fact homeomorphic to the algebraic loop space of our maximal compact subgroup. Okay, so for example, if G is C star, then this is S1, and this is just saying that algebraic loops from S1 to S1 are classified by integers. So, and what this is kind of saying is that some category of sheaves on this algebraic loop space recovers the representation theory of the dual group. And I think that you could almost imagine some version of history in which this was guessable. So if you remember the chain of equalities that I had explaining why highest weight classification was a kind of instance of Langland's philosophy, you might try to produce the dual group by considering this space of homomorphisms from S1 into K. So this is canonically highest weights of the dual group. But now you might say, okay, this is not a very interesting space. You can't deform a homomorphism from S1 into K. So we just consider all loops. So this sits inside here. And then it's, just amazing thing that, so sheaves on this space recover some category of sheaves on this space, which you can't really define unless you have this algebraic model for it, recovers the dual group. And just an important point about the geometric Zataki equivalence is that I don't know any way, if you don't know the classification of reductive groups, I don't know any way, if you give me a reductive group, to hand you back the dual group. But, so as far as I know, this is the only way of doing that. So it's kind of a fundamental thing.
Oh, excuse me. When you change the coefficients in the perverse sheaves,
yes.
Do they have to be algebraically closed?
No.
But you really do FT and then you get FT representation.
No, but you should. It's the representations of the group scheme. So it's essentially like over the algebraic closure. So what we would like to do is use this to attack questions in modular representation theory. But it's not particularly useful, or it hasn't proved so useful so far. And the reason is that there's various statements over here that we can prove that still have no, so there's statements of a very basic nature over here that have no proof over here. So an example of this is the block decomposition that I'll get to now. So this has no interpretation on the other side, as far as we know. And so we would like a kind of more zoomed in equivalence with some category of constructible sheaves, and this is provided by something called the Finkelberg-Merkovich conjecture that I'll state in a second. So this is what I'm describing now is the block decomposition of representations of an algebraic group, of a reductive algebraic group. So we have our picture of dominant weights. So here's the dominant weights. And now I just regard the Weyl dimension formula as some kind of polynomial function on this big space. And I ask, when is it divisible by P? When is this dimension divisible by P? And I assume P is not too small. And what I get is a whole lot of hyperplanes. And then I look at the group generated by reflections in these hyperplanes. And here, for example, if we do SL2, this is a trivial representation of dimension 1. This is a natural representation of dimension 2. And so we get hyperplanes at integers that are -1 mod P. Okay. And an essential point is that this group somehow controls the representation theory of our algebraic group. So this is one instance of this is in the block decomposition. So if we look at an orbit of this group on our character lattice and just look at the simple modules corresponding to dominant weights in that orbit. So here I take now I've changed my dominant weight slightly to be, here's my dominant weights. Here's the 0 weight, so this is the highest weight of the trivial representation. and now I look at its orbit, and I look at the full subcategory generated, the Serre subcategory generated by all of these simple modules. And the claim is that this is a block decomposition. This is called the linkage principle. And a great number of questions we can reduce to this principal block. So this is the block of the trivial module. And there's this Finkelberg-Merkovich conjecture, which says that this principal block is also equivalent to some category of sheaves on the Afan-Grassmannian. Okay? So this is a category of sheaves that's so-called Iwahori constructible sheaves. So in this example of SL2, we had one cell of every complex dimension, and in the geometric Satake isomorphism, the cells that show up are those of even dimension. Whereas here, it tells us to take all the cells. And so it's a much more kind of zoomed in equivalence on the representation theory of our group. So it only sees the principal block. So this Iwahori, it's the inverse image of the Borel under the evaluation map. So this is still conjectural. So I understand there's a proof in progress by Bezrel-Kavnikov and Risch. But many of the consequences that we would like to draw from this equivalence we can, and it's somehow the most useful guiding principle that I know in this subject. So it, for example, gives us an extremely good understanding of Lustig's character formula, so precisely why it holds, and why kind of questions in the singularities of this space are related to the correctness or failure of this formula. And also, I haven't done it as a slide, but this is some piece of Bezrel-Kavnikov's equivalence, which is the kind of categorified piece in the tamely ramified local Langlands correspondence. So I said before that we have these two layers. We have the unramified case, so this is geometric Satake, and then we have the tamely ramified case, and this is Bezrel-Kavnikov's equivalence, and somehow part of this is heavily related to this equivalence. So I want to finish with coming back to the very beginning. So at the start, I discussed this question of representations of symmetric groups. And I want to explain the following application, which is, so it's several years old now and has been pursued by a number of authors. But it's a new approach to decomposition numbers for symmetric groups. The picture is the following, that we pass across all of these equivalences into a topological world, and then we can compute things differently. But we still compute in algebra. So we somehow go through all these equivalences to land in a geometric world, but then we have a new algebraic way of computing things. And this allows us to compute much further and allows us to make guesses, but we still don't really understand what's going on. But I just want to show you this a conjecture that we made last year with Lustig, which is based on extensive calculations on the other side of this equivalence. So these are calculations that would be absolutely impossible to do without these kind of long chain of equivalences. So what's our problem? We start off with a partition, and this corresponds to an irreducible representation of the symmetric group over Q. And we can, it turns out that there's a so-called Specht module, which is an integral form for this representation. So if you think in terms of matrices, in principle this is given by some rational matrices, for example, or some complex matrices, but actually we can realize this in some nice way as integral matrices. And we can now reduce this mod P and ask how it breaks up. And these are called decomposition numbers when we do this. So, and this is the most fruitful way of studying modular representations of symmetric groups, is to understand how these decompose when we reduce mod P. And we can, so before I was talking about algebraic groups, and we can use some work of Donkin and Erdmann to map the determination of these decomposition numbers across to so-called to characters of so-called tilting modules for GLM. So this is very interesting. If you started studying this problem, you might think, oh, I might start off doing S3, and then I'll do S4, and then I'll do S5, and then I'll do S6. But this approach tells us, no, you should filter in a different way. You should first do 2 rows and then 3 rows. Well, first 1 row, but 1 row is trivial representation, and so I can do that. And then 2 rows, and then 3 rows, etc. Right? That's what we're trying to do. And what happens is that we go over here to some tilting modules, and these are well adapted to these chain of equivalences that I've been talking about. So this is in some sense, yeah. So what happened here was that we used this algorithm, and I programmed a supercomputer in Bonn, and it ran for 10 months and produced some data. We then stared at this data for about 1.5 years, and then finally we were able to come up with a conjecture. Okay? And also, just after it produced the data, the computer crashed. And, but now as Torge Jensen has been also involved in this, and he tells me now that we could do this calculation in about 2 weeks or something. So my code was very bad. So let me show you so this is the answer for 2 rows. So it looks very similar to the fractal pictures from earlier, and that's not a coincidence. Now 3 rows, I won't explain how we do this, but before we had this picture with, so here you can imagine you have a cone of dominant weights, and these are the alcoves of this affine Weyl group action. And so what these partitions are, these are precisely the partitions that can involve the trivial representation when we reduce mod P. So we take this module, we reduce it mod P, and we ask, is it possible that trivial representation occurs? And so these are somehow, in a way that I'm not telling you, associated to these alcoves. And now what we can do is ask, how often does the trivial representation occur when we reduce mod P? And so we get these kind of pictures. So this is saying that when I reduce this one mod P, I get 2 times the trivial representation. Okay? When I reduce mod 3. So now I will try to show you this video. Okay. So I want to give you a kind of time slice of this. So basically the time is something like NP. So I'll just play. So what you'll notice is that there's some number running along the bottom here, and this is time. And this is related to which symmetric group we're in. So it's something like NP. So if T is time, then it's P times time. Okay, so this is something like, in this particular case, if you count, there's 17. The gap between these 2 hyperplanes is 17, so this is for P equals 17. And so this would be something like related to S17, this would be related to S2 times 17, whatever that is, etc. And what I'm indicating here is that there's a certain cluster, a certain well understood cluster occur. So if we go back to these other slides. So every time I try and explain this, I fail. So I'll just continue to fail. But so this is some well-defined cluster. This 1, 1, 1, 1, 1, 1, 1. And so this, in this particular case, this would be indicated by a time variable here and then a dot here. And we think about these clusters as being some kind of billiard balls or something. Okay. So I'll just show you the video. So this is the... Okay, so something like we're able to calculate some small piece of this, and we see this, this dynamical system-like behavior. And so, for example, this is some enormous symmetric group, and then there's some cluster of decomposition numbers occurring around this ball. Okay? And so the conjecture is basically that there is some well-defined dynamical system that we define that involves these kind of bouncing balls, and that the kind of time slices of this dynamical system determine these decomposition numbers. Okay? And it seems just remarkable to me that it's an extremely discrete problem, mod P representations of symmetric groups, but that it seems to have some kind of dynamical system behavior is quite remarkable. And we have absolutely no idea why, so we cannot prove this, this conjecture. But yeah, and I would say that at the moment, the end goal is to somehow actually understand back in a geometrical world why these kind of patterns are happening, but we are far from that at the moment. Okay? So thank you very much.